studied the two possible means to implement the second order transfer function. That is via the LCR resonator, with or without the substitution of the inductance, and with a biquad scheme proposed by these authors. So what was interesting about the KHN biquad was the possibility of implementing three different functions at the same time. So at the same time, high-pass filter, bandpass filter, and low-pass filter with the same topology. This idea was based on having two integrators in multiple feedback loops. A slight variant of the KHN biquad topology is provided by the so-called Tau-Thomas circuit. The Tau-Thomas circuit is this one. So again, the idea is to implement two integrator, but the fundamental difference with respect to the KHN solution is that the first integrator acts also as a mixer. Okay, so we have multiple, let's say, signals which are hidden in the topology which is used to implement the integrator. So the integrator is not isolated like we have seen before, but it is involved in more complex feedback loops. Okay, the second integrator is independent. Okay, so it is clearly distinct from all the other signal processing topologies. And then we have this device here, which is used as an inverter. Okay, it's basically an inverting configuration in which the two resistors are equal, and therefore, by virtue of the classical non-inverting topology, the transfer function is minus little r over little r. Okay, so this is this scheme here realizes the minus one effect. Okay, apart from that, the built-in scheme is exactly the same. Indeed, we need a minus one at this point, but in this case, the minus one, the plus 1 over q time VBP was realized by this this part here of the KHN. Okay, so Tau-Thomas can be seen as a slight variant, but the concept is the same. What we can see is that with respect to the KHN, we have just two outputs which are indeed usable as respectively bandpass or low-pass filter. The high-pass version is hidden in these feedback loops because we have mixed up the other circuit and the integrator. So there is no way to extract VHP from this circuit. However, there are also some interesting advantages related to this configuration. One of these is the fact that we can control the quality factor just by playing with this resistor. So if we change this resistor with another one, we get a different quality factor. Okay, and the quality factor is linearly dependent on the value of this resistor RD. Let's jump to the whiteboard to better analyze this new topology. So, okay, just 1 second. Okay, so the circuit is something like this. And then there is a slight variant which is needed to generate also different transfer function with respect to the low pass and band pass that we have seen before. This is achieved by providing the input voltage not just to the first mixer and the integrator circuit, but also to the second part here, so to the second op-amp, via a resistor which is called R2. This is R1 and this is C1. And finally, a third input branch applied through resistor R3, which is provided to the third op-amp. This is used to somehow overcome the limitation that we have seen before related to the fact that the VHP is not available. With these additional input branches, we will see that we will have multiple opportunities to design, let's say, arbitrary second-order transfer function. Just one quick recap. We know that whenever we have a circuit like this, what we are actually implementing is the integral, okay? And generally speaking, the time constant associated to this integrator is 1 over RC. But if we obviously, if we change this resistor with a resistor which is Q time bigger, the new omega is 1 over QRC. Okay, so we are switching from this this time constant to this one by changing this resistor. Okay. Another comment is related to this part here. Okay, so the red circuit is basically given by R1 in parallel with the C1, and then the input value passing through this parallel is provided to the negative input terminal of the op-amp, and then we have a feedback loop which is running through the capacitance. Actually, we do have multiple feedback loop, but we can consider one feedback loop independently to the other, because we can apply the superposition principle and linear effects. So what is indeed the input-output relationship for a circuit like this? Well, we can apply the same machinery that we have used for the conventional inverting configuration. That is the V out over VI relationship for this red circuit here is given by the expression of the inverting topology. So minus Z2 over Z1, okay? Where Z2 is given by 1 over SC and Z1 is given by this parallel. We can also write minus Y sub I, sub 1, sorry, divided by Y sub 2, okay? So Y is 1 over Z1, and therefore it is obvious that also this relationship is valid. So Y is the admittance, okay? Z is the conventional letter to express impedances, while Y are admittances. So in this specific case, the admittance related to this branch here, so Y2 is SC, Y2 is SC, while Y1 is the parallel between R1 and C1. And the parallel of two admittances is given by the summation of the associated of the two separate conductances and admittance. So G1, which is 1 over R1 plus SC1. Okay, so this is the transfer function related to this sub-branch, which is part of the circuit. Okay, so the idea is that since these are all linear components, we can plug and add the separate effect of all the different branches. Okay, so more explicitly, what we can say is that in this circuit, we have indeed, if this is the transfer function 1, okay, which is a function of let's say j omega, we have building block, which is characterized by this transfer function, whose input is Vi. This input here is overimposed to the integration through, let's say, this branch. Okay, so we have one possible signal path which goes through this resistor and then goes at the output back to this node. So we can tentatively open the circuit here and consider this combination of effects. So through the blue, through this path, sorry, we experience the integration over -1 over SRC, which is multiplied by a factor Q, or better 1 over Q. And the input of this integration path is given by the output of this summation, because here we have the output. Okay, so we are running in this direction. V out, which is the quantity that we have at this point here, is provided as input also to R and C. Okay, so we have an additional integration effect. The output of this circuit is the combination of this integral here plus the signal originated by this path. And the signal originated by this path is VI integrated by this circuit here. So basically we have another integral which goes as -1 over SR2C, and the input is once again VI. The output of these two combinations, so the one coming from this branch and the one coming from the yellow branch. So we have the red path here, the blue path here, black and yellow. So then we enter this inverting topology. Okay, so we have a transfer function which is -1. That is minus little r over little r. This part of the topology here has two inputs, so one coming from this direction and the second coming from this direction, and the input of this second path, let's say the green one, is again provided by VI. So the green path is again VI, which enter. What is the transfer function related to this green path? Can you help me? You need basically to isolate this scheme here. R3 minus plus connected to the ground, little r here, and this is it. Okay, so what is the transfer function for this topology here? It is an inverting configuration. The transfer function is minus little r over r sub 3. Okay. And the output of the green path and this black one converge at the output. Okay, both the black path and the green one follow the same output. So this is the green path. This is still the black one. Okay. Now, where do I connect this wire here? This wire goes as input through this path. And we do have R here, and then we pass once again through the integrator. So basically, we need to connect this circuit with the input of the integrator here. So it is quite complicated combination of effects, but if you consider one effect after the other, you can complete the translation of the circuit into, let's say, Laplacian blocks. Okay, so elements consisting in transfer functions and which illustrates the global processing applied to the input. So this channel here, this one and this one are all connected to the same signal. Okay. So what is V out at the end of the day? So V out is given by the integration through minus 1 over SRC. Okay. So please remember that whenever you have an 1 over S function in the Laplacian transform domain, this means that it is an integral in the time domain. Okay. You can see it as 1 over S or as 1 over J omega in the Fourier transform domain. So this integrator here takes as input 1 over Q time V out, then second input is given by this green branch, so minus R over R3 times VI okay, minus this black path here, which is given by the combination of the black path and the yellow path. So this black path here is minus 1 over SRC time V out, because V out is the value here. And the yellow path is minus 1 over SR2C, which multiplies the input. And these are all the terms which are provided as input to this integrator here. but V out is realized by the combination of the output of this integrator and this T1S applied to VI. T1S is given by this formula. Therefore, we have minus G1 plus SC1 over SC. G1 being 1 over R1. Okay? So this is the blue path contribution. This is the red path, sorry, the green path. This is the red one. And these are the black and yellow contribution. Okay. Then you can put all this thing together and express the global V out as a function of V in to find the transfer function associated to the whole circuit. Okay, so in this case we have a mixing of V out and V input in the right hand branch of the equation. Let's try to move all V out terms on one side, all VI terms on the other side, so that we can compute this transfer function. Okay, if we do so, what we get is the following result. This expression here. Okay. As you can see, now we have plenty of degrees of freedom to configure this transfer function so that it can realize whatever transfer function we are interested in. So, for example, if you want a low-pass filter implementation, you select this combination. You set C1 equal to 0, R1 equal to infinity, which means an open circuit, R3 equal to infinity, again open circuit, and R2 equal to R over the DC gain, etc. Okay, you want to implement an high-pass filter? Well, in this case, you can. Okay, in the initial configuration, there is no way to implement the high-pass filter because you have just bandpass or low-pass output. In the new combination, indeed, you can. Okay, so the Thomas has two distinct advantages with respect to the KHN configuration. So first of all, even if you cannot achieve three outputs at the same time, three different outputs like the KHN, you can still implement all the possible combinations thanks to this additional input path. Okay. A second very useful advantage is the fact that the positive input terminal of the op-amps is always connected to the reference voltage. Okay, this means more easy and effective way to ensure the stability of the circuit. Okay, having as we have seen in the KHN case, some feedback loops which are passing through the positive input of the op-amp may be dangerous in terms of stability. Okay, you may remember that the global feedback should be always negative to have stability. Okay. This is a configuration in which the input and the output are single-ended. Okay, so you provide just single input and you pick up just one wire to get the output. In some cases, you may be interested in implementing filtering procedure on differential signals. In this case, you have quite strange and complex mirroring of the processing occurring on the negative input and the positive input through these feedback loops. Okay, interleaved feedback loops. The circuit looks like this one. Okay, but you have to duplicate the feedback loop concerning the positive and negative inputs. Okay, so this was the Thomas implementation, which is one of the options that you have for the implementation of the second project. The other option that I would recommend is the implementation of the Salen-Key filter. So the Salen-Key filter is very interesting because it allows the implementation of second-order transfer function with just one op-amp. Okay, so Thomas LCR with substitution of inductance require multiple op-amp for the implementation of a second-order transfer function. This means complex circuit, extra area on silicon. It could be much more effective and compact to realize a second-order transfer function with solutions like this one. So let's have a look at the low-pass Salen-Key filter to analyze what is the input-output relationship. So let's jump back to the whiteboard and let's sketch the input-output relationship. So Salen-Key is realized by combination of resistive and capacitive feedback loops. Let's call this resistance here R1. This is R2. The voltage, the electric potential here is Vx. Then we have a feedback loop through capacitor C3. Then we have the connection of this node to the ground through a capacitor which is C4. And then we have a buffer which amplifies the input signal by a factor which is equal to K. And the output of the buffer is provided in the feedback loop. The output of the buffer is also the output voltage V2. while V1 is the input one. Okay, we may have a common reference terminal. So V1 is this voltage drop here, and V2 is this one. Okay. We must balance the currents which are entering and sorting out this node X. So we can write this equation. The current passing through R1, which is V1 minus Vx over R1, must be equal to the current which flows in this direction through C3, this current being equal to Vx minus V2 times SC3, the admittance associated to this capacitive path. And then we have the current which is flowing in this series, okay, R2 and C4. We assume that the input impedance of the voltage buffer is so high that we can neglect the input here. So the current which flows through the series of R2 and 1 over SC4 is given by Vx, which multiplies the associated admittance. So 1 over summation of R2 1 plus 1 over SC4. We can write a second equation because the voltage V2 is controlled by the output of the buffer. So if we take the voltage here and we multiply it by K, we get V2. So the second equation that we can write is V2 equal to K times the voltage at this point. The voltage at this point can be expressed as the effect of the voltage divider consisting in R2 and C4 with respect to Vx. So K times Vx times the partitioning. Okay. It can be shown that the effect of this voltage divider, so please remember that whenever you have Z1 over Z2, the voltage at this point let's call it Vy is Vx times Z2 over Z2 plus Z1. Okay, is the usual voltage divider combination. So in this specific case, Z2 is 1 over SC4, Z1 is R2. So with some algebra, you can show that this is the result. Okay, so if you plug this result in this expression, you can compute the relationship between Vi and Vx. So, well, let me skip some of the passages so you can show that V1 is equal to Vx plus Vx R1 SC3 minus K Vx SC3 times R1 over 1 plus SC4 times R2 plus Vx, which multiplies R1 times SC4 over SC4 times R2 plus 1. Okay? So you can compute V1 over Vx by using this equation and then substitute to Vx V2 by virtue of equation number 2. And what you get is finally the relationship between V2 and V1. And the final relationship is given by this expression, which is K over R1 times R2 times C3 times C4. This is a pure number, okay, no term in S as the numerator. And the denominator is characterized by this polynomial, S22 plus S, which multiplies 1 over R2 C4 plus 1 over R1 C3 plus 1 over R2 C3 minus K over R2 C4, and the last term, the zero order term, is 1 over R1 R2 C3 C4. So this is a second order polynomial in S. This is the term which can be used to compute omega 0, while this term here is omega 0 over Q. Okay, because, this is the conventional expression that we are using to express the transfer function in terms of omega null and the factor Q, because we know that these quantities are related to the appearance of the frequency response. Okay, so interesting fact, the relationship between V2 and V1 is a second order transfer function in S, and since we don't have any term in S at the numerator, this means that this is a low pass filter. Okay, so low pass filter, second order, 1 open. You can try to find the transfer function for the high pass case. Okay, the high pass case, rather than having 2 resistors in series, we have 2 capacitors, and the feedback loop is provided by resistors. Okay, resistor R4 namely. Okay. Okay, let's have a little break, and then we will see why, even if single op-amp topologies may seem very efficient, they do have some drawbacks, and this is the reason why sometimes we get back to the 3 op-amp configuration. Okay, break.
Datemi una foto, non succede più. Io non ne parlo, quindi
deve cambiare. Deve cambiare.
per così poco.
Per così poco.
Devo fare di meglio.
No, lì tira fuori il terzo.
Sarebbe un altro titolo per il nostro video.
Che motivo?
Dico solo, no, ancora bene.
Fatta sempre così comunque.
Okay, so low pass filter through the Salen and key topology is one possibility to achieve the filtering solution with one op-amp. An alternative is provided by the so-called multi-feedback filters topologies. So the configuration is slightly more articulated with respect to what we have seen before. The idea is that these building blocks here, Y1, Y2, Y3, Y4, and Y5, are generic admittances. So even if the symbol is the one typical of resistor, they could be also capacitances. And if you compute again the input-output relationship with this configuration by using this generic symbol, what you get is an expression like this. So V3 over V1 is given by this formula here. And you see that basically by choosing Y sub 1 or Y sub 3 with reactive components, we can automatically instance some zeros at the origin. So for example, if you pick up a capacitance here, so little y sub 1 is a capacitor value. This means that y sub 1 is S times the capacitor value. Okay, so this S goes directly in the numerator of this expression. Okay, so in this way you set 1 0 in the origin. If you need the two zeros, both y sub 1 and y sub 3 will be capacitors. Okay, all these combinations are illustrated in the next plot, in the next slide. So you see, if you need low pass combination, G1 and G3 are both resistors. Okay, so actually G1 is the conductance associated to the resistor. High pass case, so two zeros placed in the origin, then you need two capacitances. And band pass case is one capacitor and one conductance, pure conductance. Okay. You need also some other capacitances or conductances because at least two capacitances are needed to implement also two poles. Okay. So these are the different combination for the multi-feedback solution. What is the difference, the main difference in terms of performances between the Salen and key and multi-feedback configuration? Well, we can say that the Salen and key topology has some, let's say, frequency issues in the sense that all the calculation that we have computed to express the input-output relationship V2 over V1 was done by assuming that the op-amp has an ideal behavior, okay? While typically, so with a flat frequency response, a very high gain. When the op-amp is a real op-amp, of course, the frequency response will degrade after the dominant pole position. This degradation may induce some problems in the low-pass filtering effect. So, for example, you see that if you pick up an op-amp which is characterized by this gain bandwidth product, equal to 0.3 megahertz, what you get is that after an initial behavior of the filter, which is the nominal one, then you have a sort of bouncing back of the frequency response. Okay? So sorry, this was op-amp C, so op-amp C is this guy. Okay? But still, the high frequency gain is slightly higher with respect to the gain that we have at this point, and certainly does not go to zero. Okay. If you select an op-amp B with a similar gain bandwidth product, again you have this bouncing back effect. If you pick up an op-amp A like this one, which is characterized by a very high gain bandwidth product, you still have the bouncing, but this occurs at much higher frequencies. Okay, but still, when the gain of the op-amp gets smaller, then the virtual short circuit and all the nice feedback loops effect that we are used to exploit, well, they somehow degrade, and this means that the ideal function deviates from the actual one. Okay, so you see, this is still minus 50 dB less than the DC gain, so still you have an attenuation, but you should handle with care this op-amp effect, because in this case, for the op-amp B case, the high pass gain is just let's say minus 20 dB smaller than the DC gain. Okay, not that much. Okay, minus 20 dB means 10 times smaller, but you are not canceling out the high frequency component totally. Okay, so there are some other considerations that we can take into account in the comparison between the silent and key topology and the multi-feedback one. Some are listed in these notes, but the most important problem for filter implementation task is related to the concept of sensitivity. So sensitivity is something that we have already studied, if you remember, when we have discussed the sensitivity of current generator with respect to voltage supply variations. Okay, but the very same concept can be applied also for the analysis of the sensitivity of circuit parameters behaviors with respect to component variations. The problem is that whenever you choose a resistor and you buy it, okay, the actual value of the resistor is always slightly different with respect to the nominal value. Okay, so you buy a 100 ohm resistor. Well, this resistor, the actual value of this resistor may be 101 ohm or 99 ohms. Okay, so what is the effect of this kind of variations, which are unavoidable, to the frequency response of the filter? Okay, so this is what can be studied by analyzing the sensitivity to parameter variation. You can find some interesting free references related to this chapter online. So let me recall that this is the mathematical definition of sensitivity. So the limit for the variation of the quantity x going to 0, okay, so very small variation of the variable x, the ratio between delta y, so the variation of the observed quantity y with respect to the nominal value of y over the variation of the quantity x over the nominal value of x. Okay, so this is basically computed by x over y times the partial derivative of y with respect to x. So, for example, y can be omega null, or y can be the quality factor q, and the x can be the nominal value of one of the resistor of the circuit components. Okay, so indeed we must study this sensitivity because the variations of components in the tau-Thomas circuit do not affect the nominal value of omega null or q in the same way that this happens for the Sallen and Key topology or for the LCR topology. Okay, so this is very important because in some cases it could be necessary to switch from one topology to the other by taking into account these issues. So let's investigate the sensitivity of the LCR resonator. So in particular, this is the combination which allows to implement a low-pass filter. So the transfer function of V out over V in, so V out is the quantity here, V in is the quantity here, is provided by this expression. So this is L1, this is R1, and this is C1. Okay, so C1 is 160 nanofarad, etc. Okay, R1 is 70.7 ohm. So these are just nominal values, and from the analysis of the voltage divider effect between L1 and the parallel of R1 and C1, we get this expression here. This is something that we have already computed. Okay. We are interested in omega null. In this case, omega null is called omega n, but basically this is the same quantity. And the quality factor. And omega null can be computed as 1 over the square root of L1 C1. Again, this is something that we have already derived a few days ago. And the quality factor is given by this expression. So we may be interested in determining the sensitivity of omega null with respect to the variation of one of these parameters. For example, the sensitivity and with respect to the variation of R1. Okay, but you see that R1 is not involved in this expression, so the sensitivity of omega null with respect to the variation of R1 is 0. Okay, but we can compute also many other combinations. So let me jump again to the whiteboard. So V1, inductance L1, C1 in parallel to R1. Then we have that V out over V input is given by this expression, 1 over S to 2, which multiplies C1 times L1 plus S, which multiplies L1 over R1 plus 1. Okay, so we have said that omega null is equal to 1 over the square root of L1 C1, and that the quality factor is equal to R1, which multiplies the square root of C1 over L1. Okay, so we have said that the sensitivity of omega null with respect to R1 is 0, but what about the sensitivity of Q with respect to R1? Well, this quantity here is R1 over Q times the partial derivative of Q over R1. So this is equal to R1 over Q, which multiplies the derivative of Q, which is this quantity here, with respect to R1. Okay, so there is a linear dependency on R1, which means that the partial derivative of this quantity here with respect to R1 is simply the square root of C1 over L1. Okay, but if you look at this expression, you can see that this quantity here is precisely Q. So this equation is Q over Q. So the sensitivity of Q over R1 is equal to 1. Okay, this means that a 10% variation of the resistance generates a 10% variation of the quality factor, etc. 5% variation, 5% variation. Okay, because sensitivity is equal to 1. We can compute also some other combination. For example, we can compute the sensitivity of the quality factor with respect to C1. This is given by C1 over Q times the partial derivative of C1 of Q, with respect to C1. Okay, so this is equal to C1 over Q, which multiplies the partial derivative of this quantity here with respect to C1. So this is R1 over the square root of L1 times the partial derivative of C1 with respect to C1. And this is 1 over 2 times 1 over the square root of C1. Okay, this quantity here can be simplified with this one. So we can replace this C1 with the square root of C1 and cancel out this term here. And the interesting fact what we get here is again the factor Q. Okay, is this guy here. So the sensitivity of Q with respect to C1 is equal to 1/2, because Q can be simplified with this Q, and we get this nice result. This is nice because this means that the 10% variation of C1 generates a 5% variation of Q. Okay, so Q is somehow insensitive to the variation of C1. What else? Well, basically we can compute all the different combinations, okay, and you can find the result in the study material. Okay, so this is an example related to the variation of the quality factor with respect to the resistor in the LCR resonator. So you see that if you change R from 50 ohm to 70 ohm, you get a similar variation of the factor Q. So Q jumping from 0.5 to 0.707. Okay. If you increase by a factor of 1,000 the resistance, you get a 1,000 increase also for the quality factor. And this is due to the fact that the sensitivity of the Q factor with respect to R1 is equal to 1. So each variation induced in the resistance turns into a parallel variation in the quality factor. While for the other quantity, we have somehow sort of insensitivity of the parameter Q and omega n with respect to the circuit parameters variation. So just 1/2 for the sensitivity of Q over C1 or L1. Well, actually, one of them is minus 1/2 because an increase in L1 generates a reduction of Q and vice versa. And the sensitivity of omega null with respect to C1 and L1 is equal to minus 1/2. Okay, and this is what we have already discussed. Since in the expression R of omega null R1 does not appear, then the sensitivity is null. Okay. Okay, this is the case for the LCR resonator, but what about the Sallen and Key topology? Okay, so the LCR resonator is based on the usage of pure component. It is a pure passive component. This means that it cannot generate any sort of amplification. We have discussed the fact that we have to add additional op-amps and to substitute the inductance and with the Antonio machinery, and we have to decouple the node from what you have as load to avoid the corruption of the load resistance with respect to the desired LCR terms. So there are several drawbacks. Why not jumping to the Sallen and Key topology? This is what it is shown here with resistors and the capacitor value. So please take into account that in this case we have the naming of the component is slightly different with respect to what we have seen in the previous case. So we have resistance R1 and R3 rather than R2, and the capacitance is C2 and C4 then rather than C3 and C4. The buffering effect can be realized with a non-inverting topology, which is this one. Okay, so the idea is that in this case we are implementing the gain K that we have seen in the previous configuration so this guy here with a non-inverting topology. Okay, so this is just a schematic depiction of the general topology, but in practice you need to use an op-amp with a non-inverting configuration. Okay. So the expression V out as a function of the input is given by this formula here. And we have this quite complex expression for omega null and the quality factor. So the problem is, what are indeed the sensitivities of the performances of this circuit with respect to component variation? Let's run some calculation. So let me resketch the circuit R1, R3, then we have C2, this is C4, then we have the non-inverting configuration, so I have to flip the plus and minus. Here it is. This is RA and this is R sub B. Okay, for this Salon and key configuration, omega null is given by this expression, 1 over the square root of C2, C4, R1, R3. And, well, of course, the gain K of the non-inverting topology is equal to 1 plus RB over RA. And the quality factor Q has a quite complex expression, which is related to the value of omega null and divided by 1 over R1 times C2 plus 1 over R3 times C2 plus 1 minus K over R3 times C4. This is a slightly different expression with respect to what you, but it is just a different way to write it. Okay, if you plug this quantity in here and you flip rather than Q, you display 1 over Q, you get exactly the same expression that you have in your study material. Okay. So okay, so this is the input and this is the output, of course. The problem is how to compute, for example, the sensitivity of omega null with respect to R1. Well, such quantity here is the partial derivative of omega null with respect to R1 times R1 over omega null. Well, there are some terms which do not depend on R1, so we can move them out of the derivation. So C2, C4, R3. Okay. Then we must compute the partial derivative of 1 over the square root of R1 with respect to R1. And then we have R1 over omega null. Okay. Okay, so this partial, well, let me copy this, C2, C4, R3. So this is basically R1 to minus 1 over 2, okay? So you multiply minus 1 over 2, and the actual result is R1 to minus 3 over 2, okay? Then you have R1, which multiplies omega null. So when you multiply R1 times minus 3 over 2 times R1 to 1, you can say that the global result is this one. So minus 1 over 2, 1 over the square root of C2, C4, R3 times R1 to the minus 1 over 2. Okay, so minus 3 over 2 plus 1. Okay, so R1 to the minus 1 over 2 is 1 over the square root of R1. So we can plug R1 in this term. And then we have 1 over omega null. Okay, but this guy here is omega null. So you can simplify this guy with this one. And the bottom line is that the sensitivity of omega null over R1 is equal to minus 1 over 2. Okay, so this sensitivity is similar to the previous one. Okay, to the one that we have computed for the LCR topology. Okay. Well, the problem is that if we repeat the same calculation concerning the sensitivity of Q with respect to R1, since that the dependency of Q with respect to R1 is much more complex with respect to the one that we have seen before, we get at the end of the day the following expression. So let me skip the algebra. So this quantity here is the partial derivative of Q with respect to R1 times R1 over Q. Okay, and the result you get if you run through all the calculation is minus 1 over 2 plus the quality factor, which multiplies this term, R3 over R1, which multiplies C4 over C2. So this is a big problem because the sensitivity of Q with respect to R1 depends on Q itself. Okay, and things may get very bad when the quality factor is high. Okay, so if the quality factor is say 10, equal to 10, and resistor and capacitors are more or less equal to each other, then the sensitivity of Q is also in the same order of magnitude. Okay, this means that a 1% variation of the resistance may generate 10% variation of the quality factor. Okay, so this is very bad news. Let's jump back to the sensitivity calculations. So this is again the expression for quality factor and omega null, and these are all the different sensitivities. Okay, so this is bad. This is also quite bad. Okay, we have the sensitivity of the quality factor with respect to the variation of C2 and C4. This is also quite bad. Okay, so the sensitivity of the quality factor with respect to the variation of the gain of the non-inverting topology is Q times the gain. Okay, so if the quality factor is high and the gain is also high, then we may have some troubles. Okay, and similarly we have some other detrimental effect. So just in few cases the sensitivity is relatively small or null. Okay, but in many combinations the sensitivity could be a very bad problem. In this case, you see an example. So what's happening when you are varying this resistor here from 1 kilo ohm to about 20 kilo ohm? Okay, so you see that there is a quite huge variation in the gain, and definitely a very important variation in the quality factor, while the frequency, the cutoff frequency, more or less is the same. This means that omega null, it is almost completely not affected by the variation of RB. And this is consistent with this calculation. You see that if the sensitivity is calculated as a function of RB for omega null, then what you get is 0, okay, as a result. Now there is a sort of a problem that we have to take. So we have analyzed the sensitivity with respect to the variation of the parameters. So the problem is there a way to exploit the degrees of freedom that we have in the design stage to minimize the sensitivity effects with the proper tuning of the parameters? Well, the answer is yes. And this can be shown in the following way. So basically, we have said that these are the expression of omega null and the quality factor for this Sallen and Key configuration. So now we have to set two parameters, two values for the transfer function, and we have the availability of multiple circuit parameters, C2, C4, R1, R3, beside RB and RA. So multiple degrees of freedom to set just two parameters. So when we handle a situation like this, one way to proceed could be to simplify the design stage with a sort of, let's say, lazy procedure. Okay, so the lazy procedure goes this way. Okay, I will pick up all resistors equal to each other. And I'll do the same for the capacitor values. C2 and C4 shall be both equal to a given capacitance C. This simplifies a lot the expression. Very dangerous. Okay. Okay, so in this lazy design strategy, omega null is equal to, since C2 is equal to C4, here we have C22 and here R22. So omega null is 1 over C times R, right? And Q is 1 over RC plus 1 over RC, but also omega null is 1 over RC. So we can divide numerator and denominator time 1 over RC, and this simplifies the expression a lot. So Q is equal to 1 over 2 plus 1 minus K, right? Because this is 1 over RC, 1 over RC, 1 over RC times 1 minus K, and this is 1 over RC. Okay, so this is Q. Well, actually, Q is then 1 over 3 minus K. Okay, simply. So, so basically, the quality factor is controlled by the gain of the non-inverting topology. Okay, we can flip this expression and say that K must be equal to 3 minus 1 over Q. Okay, so in this case, what is the sensitivity of the quality factor with respect to R? We can use this expression, okay, but R3 is equal to R1, C4 is equal to C2, so the square root here is the square root of 1, so 1. So the sensitivity in this lazy design strategy is equal to minus 1.1 over 2 plus Q. Again, in this case, if we suppose that the quality factor is equal to 10, then this implies that the gain K must be equal to 3 minus 110, so 2.9. And the sensitivity of Q with respect to R will be 9.5, so minus 1.2 plus 10. Okay, so minus 0.5 plus 10. So this sensitivity is huge. Okay, definitely this could be a problem. If you are still with me, let's see what happens if we choose a different solution. Let's call the new strategy the smart one. in this case, we tolerate that C2 is different from C4, but we select K so that it is equal to 1. So R1 is equal to R3, but C2 can be different from C4. K is equal to 1. Okay? Let's take once again this couple of expressions. So what is interesting is that if K is rigorously equal to 1, then 1 minus K is 0. So the quality factor is omega null over 1 over R1 C2 plus 1 over R3 C2. I think that we need a break before running through the next calculations. Okay.
Passa. Va bene? Passa di tutto.
Okay, so let's see why the smart strategy is smart indeed. So the quality factor is omega null over 1 over R1C2 plus 1 over R3C2. The omega null value is still this one. The sensitivity is, let me recall the previous result. The sensitivity of Q with respect to R1 variations is given by -1/2 plus quality factor time square root of R3 over R1 time C4 over C2. So we can plug this result here, and then we can substitute the value of omega null with this quantity. Okay, if we do so, the total expression for the sensitivity is this one. So -1/2 plus the quality factor, which is in turn omega null, which is this quantity here. So 1/. C2 times C4 times R1 times R3. And then we have the second part of the quality factor expression, so the denominator here. So 1/. We can collect 1/C2 because this term multiplies 1/R1 and 1/R3. And then we have the square root of this quantity. Okay, R3 over R1 plus times C4 over C2. Okay, let's apply some simplification. So, for example, we can cancel out this R3 with this term here. Then we have that this C4 here can be cancelled with this one. Then we have the square root of C2 times the square root of C2 divided by C2. So let's get rid of these three terms. And yeah, this is it, I would say. Okay, so after these simplifications, the sensitivity of Q with respect to R1 is -1/2 time 1 over the square root of R1, and we have another 1 over square root of R1 term, so this is plus 1/R1, okay, time this quantity here, so 1/R1 plus 1/R3, right? This is -1/2 plus 1/R1. This quantity here is R3, well, it is 1/R3 plus R1 divided by R3 times R1. Please check if I'm right or wrong. Then you can simplify this with this and finally get the final result for the sensitivity. So the sensitivity of Q with respect to R1 is -1/2 plus R3 over R1 plus R3. This is quite interesting as an expression, especially when you pick up R3 to be equal to R1. Because when R3 is equal to R1, this term here is equal to 1/2. So by plugging this in this expression, what you get is that the sensitivity gets equal to 0. Okay? So the huge problem that we have had in the previous configuration, by properly exploiting the degrees of freedom that we have, can be turned into a null problem. Okay, so quite interesting indeed, the flexibility in the design of the Allen and Key configuration. However, there is always a trade-off. Okay, so even in this case, we are trading off the capability of achieving a very small sensitivity in exchange for something else. Let's review what is this this problem. We have said that we can play as designer with R1, R3, C2, and C4. And in this case, the gain is forced to be equal to 1. And we have to control two parameters, omega null and Q, by properly tuning these two guys. This quantity. If we set R1 equal to R3, we are losing 1 degree of freedom. Okay, so if R1 is equal to R3 and this is equal to a value, generic value R, this means that the omega null quantity will be equal to 1 over square root of R1 times R3, so square root of R22, which is R, times the square root of C2 times C4. Okay, this is for the Allen and Key configuration, of course. Quality factor, in this case, when K is equal to 1, is omega null over 1 over R C2 plus 1 over R C2. Right? So this is omega null over 2 RC2. So this is 1 over 2 times omega null times R times C2. Okay? Omega null is this quantity here. So the quality factor is 1 over 2 times 1 over R square root of C2 C4 times R C2. Right? I'm plugging this result in here. Okay? So this term goes away with this one, and the square root of C2 here can be applied to the numerator. So the bottom line is that the quality factor is 1 over 2 times the square root of C2 over C4. We can flip this expression and say that 4 times Q to 2 is equal to C2 over C4. Right? What's the problem in this expression? Well, there is a practical manufacturing problem, in the sense that when the quality factor is, again, equal to 10, this means that if we plug this result, so this is an hypothesis, okay? Suppose that you want a quality factor equal to 10. You have to plug this quantity in this expression, and it follows that C2 over C4 should be equal to 400. Okay, so the capacitance C2 must be 400 times bigger with respect to C4. It's not easy to have such a huge difference between capacitance in either an integrated circuit but also in a discrete one. Okay, so typical value of capacitor that you can buy, okay, are in about 3 order of magnitude. Okay, so from, let's say, some tenths of nanofarad down to relatively few picofarad. Okay, but if the quality factor that you need to implement is even larger than 10, you can see that there is a power of 2 term which generates huge factors between the two capacitor values. Okay, and a slight discrepancy in the value of one of these of the capacitor may generate a quite consistent change in the quality factor. So this could be a problem. So the Sallen and Key solution combined with the smart strategy may be very effective in minimizing the sensitivity of the quality factor with respect to the resistance variation, but for high Q implementation, well, this is still a problem. That's the reason why typically Sallen and Key configuration are not used for high Q transfer function implementation. Okay, this discussion is thoroughly described in the study material. Okay, so in the study material you can find this highlighting. So the effect related to the selection of k equal to 1, so that some sensitivities goes down to 0, like this one. Okay, if R1 is selected to be equal to R3. There is still this limitation related to the sensitivity of the quality factor with respect to the variation of the gain. Okay, but to be honest, this quantity here, when k is equal to 1, is not really an issue. Okay, because achieving a unitary gain factor is very easy. Okay, you just connect the buffer in this way, and you get a unitary gain buffer. Okay, so and in this case the variation of k are minimal. Okay, you have no resistor whose value can change in the end. Okay, so this expression may sound bad, but the truth is that the variation of k are so small that we can easily neglect this. Okay, when you use a unitary gain buffer. So these are the good news. Okay, so so with the perfect op-amp k will always be precisely 1. This is what I was discussing. Take into account that, however, real op-amp op-amps have finite open loop gain, so the reduction of k may be not non-negligible. But nevertheless, I mean, this is quite interesting. The big what is also interesting is that you may wonder, so we have said that our goal is to have R1 equal to R3 in order to set the sensitivity equal to 0. But what happens if we take into account the fact that we can never be 100% sure about the equality of two different resistors? Okay, so R1 could be different from R3 even for a small quantity. Well, if you suppose that you may experience a 5% variation in the resistor value, and you suppose that you are in the worst possible situation, that is R3 is incremented by this 5% factor, and R1 is decreased by the same quantity. Well, if you run into the calculation and you say that, let's say R3 is 1.05 R nominal, and R1 is 0.95 times the value R nominal, you plug this quantity in here, then R nominal goes away in the simplification, and you get that the final result is that the sensitivity is not null anymore, but indeed is very small. Okay, 0.025. A 10% variation or a 5% variation in the value of the resistor generates a very small variation in terms of Q values. Okay. Okay, so then it is discussed the problem related to the sensitivity of the different parameters. It is discussed the fact that all the sensitivities now are either equal to 0.5 or 0, apart from the sensitivity with respect to K, which we have said it's not really an issue because K is equal to 1. However, there is an important discussion related to the quality factor. So here you can find some numerical examples related to the two different strategies. So you see in this case, R1 is equal to R3, but also C2 is equal to C4. The gain is different from 0, is actually equal to 2. So this is what we have called the lazy strategy, okay? Lazy strategy implementation. The gain is equal to 2 because the gain K is 1 plus RB over RA. In this case, K is equal to 1. Okay, because we have the unitary gain buffer configuration. The two resistors R1 and R3 are equal to each other, while the capacitors are different. So this is the so-called smart implementation strategy. Okay. The two nominal responses for the two implementation are this one. So in the first case, we have K, which is equal to 2. So we have a DC gain, which is equal to 2. So we have 6 dB in the dB plot. Okay, 6 dB means a factor of 2. Okay. These are the nominal values, same omega null, same quality factor, so same overshoot. This is what happens when you apply random variation around the nominal value to the resistor and capacitors. So you suppose that capacitor value can vary up to 5% plus or minus, and resistors can vary up to 1% plus or minus. This is the result of the lazy strategy. This is the result of the smart strategy. You see that there is a bunch of curve now. There is no more just the nominal one. Okay, because indeed the parameters are varying with respect to the nominal values, but the width of this bunch of frequency responses is much smaller in the smart design strategy, which means that in the smart design strategy we are less prone to the variability of the component. Okay, the similarity between these curves and the nominal one, it is much higher with respect to the huge variation that we can experience if we apply the lazy design strategy. Okay, so indeed when you run the simulation of analog circuit design implementation, you cannot take into account just the nominal value. You must take into account the fact that you may have variation in the nominal performances. So you run what are typically referred to as Monte Carlo simulations. Okay, so tentative simulation with variation with respect to the nominal value of the parameters. In this case, we have run 100 different simulations. You can. This is typically sufficient, but in some cases you need even more runs. Okay, so what did we give up with this smart design strategy? So we have a more faithful transfer function with respect to the nominal value, but the biggest issue is given by this formula. Okay, so huge capacitor value ratios. Okay, which can be as high as 400 if the quality factor which is needed is equal to 10. Sensitivity of the Thomas filter. Okay, the good news is that we will skip all the calculation. Okay, so I want to tell you just the final result, which are very simple. They are listed here. Okay, so this is the expression for the omega null and the quality factor. And so this represents the dependency on the circuit parameters. And you see that such dependency is relatively simple. Okay, it is in practice the sensitivity is between -1/2 and 1, depending on the different parameters. But as a matter of fact, these are, let's say, values which can be tolerated. Okay, so no dependency on the quality factor or gain. So the sensitivity in the very worst case it is equal to 1. So typically the Thomas configuration can be privileged when we have very high Qs. Okay, so when we have very high Q, either you can apply the Thomas machinery or the Sallen and Key with the smart strategy. But the Sallen and Key with the smart strategy means very large capacitor value ratios. Okay, so usually you pick up the Thomas circuit. Okay, this is just a recap of what we have seen so far. Before concluding this session, I want just to give you some other hints. We have neglected so far the problem of the non-ideality of the op-amps. Just we have just quickly reviewed what happens with the Sallen and Key configuration. But indeed, the op-amp non-idealities can be an issue for all the configuration that we have seen so far. And there are some, let's say, practical rules, let's say rules of thumbs for the selection of the op-amp, depending on the filter response that we needed to implement. And one typical way to select the op-amp is to pick up an op-amp whose frequency response is sufficiently far from the frequency response of the filter that we wanted to implement. Okay, so you compare the frequency response of the op-amp, you draw the frequency response on the same baud plot with respect to the filter response that you want to implement. So let's say this blue curve is the frequency response of the op-amp, while the red one is the frequency response of the filter that you want to implement. So in this case, a filter with a quite high overshoot, so high quality factor, and with a DC gain which is capital A sub null. Okay, so you compare these two curves and you try to keep the blue curve far apart from the red one. Okay, if the distance is in the range of 40 dB, you are typically safe from the non-ideality of the op-amp in the filter implementation. Okay, so 40 dB means 100 times bigger with respect to the maximum overshoot of the filter. Okay, is it clear? Okay, so op-amp, the op-amp frequency cutoff characteristics should not interfere with the frequency response of the filter. Okay, some other consideration may be related to the slew rate also of the op-amp. You can find some interesting notes here. So basically you relate the slew rate to the peak-to-peak frequency and the cutoff frequency of the filter to get an adequate response. Okay, this is related to possible distortion effects. Okay. So this is a practical numerical example related to what happens depending on how you pick up the cutoff frequency or the gain bandwidth of the op-amp. So the same circuit that we have seen before. So second order transfer function, if you select a 100 kilohertz gain bandwidth op-amp, you see that there is a huge difference on the picking of the frequency response with respect to the case of 10 or 100 megahertz gain bandwidth. So 10 and 100 megahertz gain bandwidth practically are undistinguishable, while if you jump to the 100 kilohertz case, you have a clearly distinct behavior. Okay, this is such difference is not tolerable typically. You are changing the cutoff frequency a lot. Okay, you see the cutoff frequency is around 10K in this filter, while it is much less than that, maybe 7 kilohertz in the 1 megahertz in the 100 kilohertz gain bandwidth case. Okay, so the distinction between these two configurations is just in the op-amp behavior. Okay, so the op-amp indeed matters. Okay, so the selection of the op-amp is also an important step in the circuit design. Okay, just some let's say, preview of what we are going to see tomorrow. So far we have discussed just the second order filter implementations. But of course, in some applications, the selectivity provided by second order transfer function is not sufficient. So in some cases, you want to implement a very selective filter, and to do so, get rid of the frequency component which are above the cutoff frequency. And to do so, you may need higher order filters. The good news is that in terms of practical implementation, higher order filters are just realized by chaining second order transfer function or first order transfer function. Okay, so once you have learned how to implement second order transfer function and first order transfer function, basically you know how to implement also higher order transfer function. The only issue is how to select omega null and Q to have the proper selectivity effect, but this is achieved by applying purely mathematical procedure. Okay, the one derived by Chebyshev and Butterworth or Bessel. Okay, but there are fixed procedure that you can apply, or actually you can use PC program to derive omega null and Q values automatically. Okay, there is no, let's say, no problem in that. Okay, it's a pure mechanical procedure. Okay, what is truly intriguing and difficult and challenging is selecting the proper topology for implementing the different second order elements in the chain. Okay, so tomorrow we will review some of the most famous higher order filter design procedure, one by Butterworth, the one by Chebyshev, and then you will have all the elements to design your own filter. Okay, thank you very much for your attention, and see you tomorrow.